Okay, so there's an example here in the slides, which you should look at. Maybe we'll release that as a separate video after you've looked at the main conceptual stuff. I could talk about that in one of the office hours. It's got a kind of worked through example of driving home scenario, where you're trying to predict how long it'll take to get there, to get back, and you use TD predictions to kind of update that model. So it walks through some of the examples of those numbers. So take a look at that. The main difference I want to emphasize for the difference between Monte Carlo and TD methods, so we can get into the actual decision-making optimization algorithms more quickly, is this idea at the end. So you're driving, you're trying to estimate how long it's going to take you to get home based on the evidence. And if you're just doing samples of different policies going forward, you're updating your numbers every time you get home. You figure out how good your estimates were and you update them, right? So your estimate of the true time to get home of each of these stages kind of converges after you've encountered these situations enough times. Since they only get updated when you get to the end, the updates all actually happen after the fact, but in a larger jump. So it makes these big steps towards being correct, because each of these estimates is being updated after the fact, because now you know the actual update, the value. And so for this state, you update it. In TD, you don't get the correct update, but you get it right away, right? So we figure out, an update on this estimate of the time for each of these states once we find out that it's longer than we expected, right? So here we had an estimate of it would take us this long to get home, and once we got here, we realized that it must be longer, and so this it must be shorter, and this gets pulled down. And these will keep moving up and down as we do multiple episodes and we loop around, starting over many times. But it means that your model gets updated as you go. So this is an advantage because you can improve your model before you actually know the final outcome. So in a game or a domain where you could return to the same state, this is actually very useful, right? Because maybe you're still coming back to the same state and you still haven't figured out if you won the game or not. So walking around a maze is an example. All the things you guys will be doing programming in this term will probably be like that. Chess or something would not be like that, right? Because that state would never return again because pieces are off the board. But a lot of domains you can get back to the same state or similar states. And so if you can't learn while you're playing, that's a bad thing, right? So that's one of the main advantages. It also converges faster than Monte Carlo. So we can kind of see that in this very simple domain. So we have an MDP here, which is a random walk. You start off in state C, right? And you've got some random probability of stepping left or right every time, right? So your policy is just flip a coin, go left or right based on the coin. And you get no reward at all ever until you go right and you get here and you get a 1, right? And otherwise you get nothing. And if you end up here, then you stay there forever too. So the square boxes are absorbing states. That's where you end. But you only get reward if you go to the right multiple times. So how do you evaluate that? How do you evaluate how good it is to be in state A given this policy, right? It's pretty bad to be in state A because you have to get lucky this many times to move to the right because you can't change the policy at this point, right? But eventually you get a value function like this saying it's really good to be in state E and really bad to be in state A. So we know that. That's what it should be. We can solve it exactly with value iteration. If we want to try to estimate this with TD, the one we've shown where we do one step update, then let me move a little bit. What do we end up with? We end up with so we get the state, all the estimators for each of the states. So here's our value function, literally the entire value function. There's only got 5 states. And the lines, it's a bit tricky to read it, right? This is our estimator at the beginning, right? It's just a flat line. We start off, all of them have a value of 0.5, right? We said value function is initialized to 0.5 for all of them, so that's what that means. And then each line is the new value function after that many iterations. So after one episode where we've played the game and gotten to one of the absorbing states, we learn something, right? We learn that state E is really good, and state A is not so good. And as we do more episodes, we get a better value, and eventually we learn this line that says they just basically increase linearly, and here's the slope. That's the value function is just a line through that. Even after 100, we've not got a perfect one, but we've got a good approximation of it. So using this domain and TD with different values, the one parameter, right, is this alpha, right? So you've got this alpha which weights how much you take into account new information, right? So once you get the new reward and you've learned something from your experience, how much do you update that state, which is different than the discount factor, right? Think about that. What's the discount factor? Hand up, you in the back. Discount factor, right, is that's the future, right? This is about future states, saying that future is less important. Alpha is about weighting new information, right? Right, so there are different parameters. And we're using a fixed gamma here. And what we're plotting here is the root mean squared error, so how far we are off from average over all the states. Okay, yeah, so we've got an average of how far are we off on the entire model, right? So here you could do the root, you could do the error between your current line and the true line, right? You could come up with these differences, right? And then you could average for all of your differences and take the squares of all the differences and the square root of that to give you your root mean squared error. And that's the value we're plotting. And what we're plotting here then is all the different performances of these two algorithms, but with four different settings for Monte Carlo and 3 different settings for TD. This is a good example of ways to compare algorithms on any domain. We're going to have a couple different types of plots like this. It could be RMS or it could be reward, where you're going to plot your algorithm with a couple different parameter settings and all of the different algorithms, where the x-axis is you're learning more. So you're doing this thing 25 times, 50 times, 100 times, right from the beginning, and then plotting them together, right? And the main thing we're taking out of this is what, right, is the performance, how quickly it gets there. So they all get to better policies, right? So they're getting the error down to 10% or 5%. TD is getting better than Monte Carlo, but if you ran it long enough, you'd expect maybe Monte Carlo is going to converge and get to one of these, right? They all, like we said, if we're doing, did we get that yet? No, we're about to talk about that. That there are certain scenarios where Monte Carlo is guaranteed to converge, so it'll get to the perfect thing eventually, but how quickly? And we see that TD gets there much quicker, right? Because it's updating the states as it goes, and it knows how to assign the reward to local states, whereas Monte Carlo is always assigning that what it's learned to all of the states in the entire kind of trajectory, right? And so what's the correct value of alpha is something that just has to be done by trial and error or maybe by a domain. But when you're kind of trying these out, you have to experiment and try different ones. It's not like lower is better or higher is better. There'll be a sweet spot for every particular domain, and that's just going to be an aspect that happens in many different algorithms in reinforcement learning. That's why we like ones that have fewer parameters, because this is really something you have to set, and it seems good. This one learns really quickly, but it doesn't get to the same value, and it's converged to something worse than this one. And that's a general rule in many optimization problems. I'm sure you've seen that in other things, in other courses, that anything where you're improving incrementally, usually slower is better in the long run. The smaller steps you take, the better answer you'll get. But again, it depends how long these take to run, right? If you've got to get this be responding in real time, and this takes 5 minutes, then that's just too long. And maybe this is good enough for the performance you need. If you're doing like medical studies and you need to give people predictions and you can run this thing for a week, then the highest accuracy possible is important and you can wait a little longer. So one additional thing then to talk about this with is another way to do these updates. So rather than just running each episode separately, there's a general approach called batch updating, which will actually come up again later when we get to deep learning. The current new methods, which is that kind of similar idea that you take the sum of all of the experiences you've seen so far, so all of the episodes that you've experienced so far already, and keep training on them over and over. Because remember, because of alpha being small, we alpha being less than 1, each time we learn something from a series of states and actions, there's more you could learn, right? So you're only moving a step towards improving your value function. So retraining on the same set of experiences actually moves you again towards it. Obviously, if you do that too much and just train forever on the same history and never try anything new, you'll converge to basically optimizing that set of experiences, right? Which isn't what you want, but doing it many times and kind of squeezing every bit of experience out of these series of states and actions is what batch updating does. And so you can compute these updates as you're going, but you only actually update them once you get to the end of the batch. And so the approach we're going to use here is that you treat the entire history, everything you've seen, you basically update on all of those episodes again every time, and then you update the values so you don't use your new estimates until you're finished going through the entire batch again. And so for batch updating, they have results showing that if you fix the alpha, so for a fixed alpha, Monte Carlo converges to some answer, and so does TD, right? So as long as you're basically re-experiencing all of these, right? So every time when we get to round 26, we retrain the model, or basically compute new updates for every one of the previous ones we've seen, including the new 126, and we add all of those to V, again, using alpha, and we do this every time. When we do 27, again, we find all the previous ones. That's the batch in this approach. The batch could be anything. It could be subsets of this, but in the current way, we're saying using all of the previous episodes. But as long as you're not changing alpha as you go, then both of these methods are proven to converge, as long as alpha is not too big. But interestingly, they converge to different answers. So the idea that they're both kind of converging to optimal is not kind of global. It's not that well defined, right? So we get the same MDP, and after every episode, we're going to do like I was saying. And so if we use batch training for a particular alpha, we didn't say which one that was here. Here's the plot for the Monte Carlo method, kind of improving over time, and that really does get better, and we have guaranteed that they will converge to something eventually and stop changing altogether, but they're not going to be the same answer, right? So if we think about this logically, what's the Monte Carlo method going to converge to, right? It's using the experience that it's seen and kind of minimizing those differences. So what it converges to in the data that gets the kind of lowest error is going to be that it'll know that it'll set VA to be 0. So I guess what we're talking about here is just, if you just talk about the value for this particular state, what's the value of this state, right? The Monte Carlo one is going to say 0, because when you're here, you get 0 a lot of the time, and that dominates the law of large numbers eventually, washes out everything else that happens, and this becomes an estimator of 0, and that's what it converges to, for this particular state. So its value averaged over all the states is going to be higher than 0, because some of them are higher. But TD doesn't. It says the value of A is 0.75 because you get one, but there's a chance of it of still getting some value. And what this does is this is maximizing a different notion, right? So Monte Carlo is maximizing essentially mean square error so that you minimize the prediction error for getting those values. But the TD algorithm is optimizing for the maximum likelihood of that model, which we haven't talked about, but is essentially giving you a weighted probability of getting some value over time. We should have some way to explain that in more detail. But they converge to different values is important to know. So other advantages then, or it kind of includes stuff we've talked about. TD is going to converge more quickly because it's estimating this change in the value across time, right? So the Markov chain approaches don't really gather a lot of information about consecutive time steps because it's always looking at the entire process. So it's really kind of estimating the lowest common denominator of an entire chain. And this means that TD is going to improve kind of more broadly across the entire set. And the fun thing is that it's not building a model, right? So it's not using like dynamic programming or in a sense even Markov chain that is trying to learn those probabilities in between them. It's really just saying, if I'm in this state, did I do better or worse? It's trying to optimize those little estimates of the value of being in a state without saying what's going to happen next. It just says, after that, I trust my model going forward. And that tends to be a very powerful approach. So it has a very narrow update because it's looking literally at just the action that it took. And it's not even going very deep, right? Every update is happening literally over a local chain in the tree, which you could imagine as being the same chain in everybody's tree. But TD basically updates that and stops, whereas Monte Carlo can't update it until later. And in dynamic programming, you have to have all the other ones to normalize it properly. So they're also computationally congenial, but what we mean is they're computable, right? Those updates are all local, right? So that's important. So programming it is quite easy, right? Computing those updates, writing them down, storing them is something that is great for computers. And it doesn't require you to store the entire history and the vector of everything across time because everything's local. And that is one of the reasons that these approaches kind of very inspiring at the beginning and kind of the base of a lot of things. Yeah, and I guess a drawback of the Monte Carlo methods is they're really trying to reduce the error on all the past data, assuming the future is just like that, whereas something that uses a temporal difference is really trying to learn the difference of things as they change over time, not really focusing on learning a perfect model. Okay, so the next thing then is to talk about an algorithm that actually takes actions on these domains.